at Reading. He's in my school, but in the meteorology department, and he's going to talk to us about real stuff, real observation of mesoscale structures. Thank you. Thank you.
Okay, thank you, Beatrice. So, as Beatrice said, I'm in the meteorology department, and so I'm going to be talking about some aspects of cyclones, intense cyclones, and the fronts embedded within them. The links with, particular structures in the wind fields, and then thinking about how that relates to the usual understanding of the systems in terms of balance, flow, and so on. So here's the outline of what I want to cover. I want to talk about just straightforward cold fronts to start with, because that's a kind of familiar example to many people, and links in with frontal geostrophic theory. Then I'll talk about bent back fronts, and I'll explain what those are in a moment if you don't know what those are. And then, but essentially they have very tight curvature as well. And then I'll say a bit about semi-geostrophic theory, which of course will be coming up on Thursday in particular. There's a whole sequence of talks about semi-geostrophic theory. And then I'll talk in particular about a whole host of aspects observed in some of these cases which we don't really understand very well, as a kind of motivation for things to look at in the future. So here's a typical cyclone. In fact, it's the one I'm going to be using as an example quite a bit. This is a satellite image. You can see the cyclone centre here over the north of Scotland. It was actually a very rapidly developing cyclone. The usual jargon there is it was a bomb, but it developed about twice as fast as the usual definition of a bomb. And you can see the usual meteorological analysis here with a surface pressure pattern and the various fronts indicated on. So this is the cold front here, the kind of thing I'm going to talk about first. And then also this front marked in curling around the cyclone. That's what's often called the bent back front. And then the bottom one here is a simulation. It's actually from forecasts using the Met Office model, and the red lines are potential temperature contours at low levels. So you can see the gradient along the cold front. There is quite a gradient around the bent back front, but I haven't used a very high contour interval here, so you can't see many contours packed in. Okay, the observations I'm going to talk about as I go along have been collected as part of a large field program and project that's just finished. Actually, it was called Diomet, and the main focus was actually on cloud processes within storms and their effects on the dynamics. And I'm not really going to be talking about the cloud side of things at all here. But the lead of the project was Geraint Vaughan, who's also the NCAS Weather Director, so National Centre for Atmospheric Science in the UK. And I was the PI for Reading. But there were a number of universities involved, and the Met Office as well. So here's one of the cases. This was a case where there was a particularly intense cold front, and this on the left is actually real data. This is from the radar network over the UK, and you can see the cold fronts basically along this north-south axis. The tight red line here is kind of like line convection, so the most intense rain rate along the front. You can see a little bit of a kink here around Cheshire. In that area, and tracking across the UK there are actually 4 tornadoes on this front. I'm not going to be talking about those very much, but this is actually a forecast with the 1.5 kilometre version of the Met Office model. So it was a forecast actually run in real time at the time. You can see it's almost a 30-hour forecast, but there are many aspects which are very close to those observed, including this intense part of the front and the kink there. The contours behind a mean sea level pressure, and so obviously you can see the V shape in the contours associated with the front. This was an observation across the front. So Capel is over North Wales, and this is the front here. So height going upwards. You can see how the change in wind speed and direction is extremely sharp. This is obviously the surface front down here, but you can see it's a kind of sloping interface through the atmosphere. And then these are some surface observations near Manchester. So this funnel cloud was actually observed at the time of the passage of the front, so not quite a tornado, but I don't think any of them were actually seen, the actual tornadoes, so often the case. So you can see, particularly in temperature, for example, the time axis on all of these is 24 hours. You can see how abrupt these kind of fronts are. The precipitation obviously concentrated right on the front itself. Even the pressure has some kind of jump on it in this case. That's not always the case by any means with fronts. So the way people typically think about fronts or the development of the fronts in the atmosphere is to go back to frontal geostrophic theory or semi-geostrophic theory, as Hoskins and Brereton called it at the time. Now people tend to call it frontal geostrophic to distinguish it from a more general semi-geostrophic theory. So the idea there is that we could form a very intense gradient in a conserved variable like potential temperature, but quasi-geostrophic theory or just deformation in a large-scale flow would only give us an exponential increase in that gradient with time. But the main thing that Hoskins and Brereton strove to show in the beginning is that you could form a discontinuity in a finite time, and their argument as to why that might occur. And in frontal geostrophic theory, they make use of the fact that the front is obviously very anisotropic. It's got a very long axis compared with the gradient region of gradients across the front. And then they use that information. Basically, it's to do with the advection operator. So the cross-frontal advection is much greater than the advection along the front. And if you scale the cross-front component of the momentum equation is in this direction, so in the x direction. So if you compared accelerations to the Coriolis acceleration, you would find out that that ratio, essentially the Rossby number, is much less than 1. So the along front wind is very near geostrophic, but that's not true of the across front wind. And here's a typical scenario. So this is a shear frontogenesis scenario. You could have a deformation one, but they're similar in some respects. So here we've got the warm air on this side, cold air on that side, and a strong shear in the meridional direction. And the shear is continuously increasing the gradient here at the front, and then the wind stays near thermal wind balance all the time, and so that implies that we need a cross-frontal circulation in order to maintain that thermal wind balance.
Can you explain where's the shear? Is the shear of the...
Oh, shear, sorry, you probably can't see these arrows very well. So the main shear is that the main flow is northwards here and southwards on this side. But then there's a cross-frontal circulation. So here's missing out a lot of things here, but so the along front component of the momentum equation has an acceleration where the d by dt is the Lagrangian derivative but following the full flow, but the along front momentum has been approximated by its geostrophic part, and then the pressure gradient force here has been kind of hidden in the fact that we've only got the ageostrophic component of the flow here, because the geostrophic part cancels out with the pressure gradient. We also, if we assume it's in hydrostatic and anelastic balance, then we have a thermal wind balance between vertical gradients in the geostrophic flow and the horizontal gradients in the buoyancy. And so the crucial thing here is that the deformation or the shear continuously is increasing the gradient, but in order to stay in thermal wind balance, that implies that we need a cross-frontal circulation. And people, Soren Eliasson first derived this equation. I'll show it on the next slide. But you can obtain it by thinking about the fact that the rate of change with time of thermal wind balance is 0 in order to maintain thermal wind balance. And so if you just took the Lagrangian derivative of this thermal wind balance here, you would obtain the Soyer-Eliason equation. And here's an example. So this is a quasi-geostrophic version of it. So in the quasi-geostrophic theory, you get an elliptic equation for a stream function variable. The stream function is in the cross-frontal plane, so u is the cross-front direction, w is the velocity upwards, the vertical velocity. And the quasi-geostrophic version is obtained by taking the rate of change of thermal wind balance following the geostrophic flow, not the full flow. Okay. And if you invert this equation to find the stream function, then for that shear frontogenesis forcing that I showed you in the schematic, you end up with a fairly uniform cross-frontal circulation like this. So this x here is going from the cold to the warm side of the front, and we've got a thermally direct circulation with ascent on the warm side, descent on the cold side. Now in semi-geostrophic theory, where we can advect by the ageostrophic flow as well, you end up with a very similar cross-frontal equation, but it's only similar if you change to geostrophic coordinates. So here the small x is the distance across the front in physical space, and then you're adding this Vg over f term. The height variable is not changed in this coordinate transformation. So, and although some of these factors outside the derivatives here are actually different from in quasi-geostrophic theory, you generally obtain a rather similar looking circulation, but the difference is now it's in geostrophic coordinates, not physical coordinates. So you have a fairly uniform cross-frontal circulation. But if you transform into physical space, what you typically find is that the bottom of this circulation concentrates in the region of the front. So we've got an increasing vorticity with time at the front. These dashed lines indicate absolute momentum surfaces or surfaces of this constant variable capital X. So we can use the same kind of thinking or machinery as quasi-geostrophic theory, but when we transform into physical space, we find concentration of variables where the vorticity is increasing. And that's the basic mechanism behind frontogenesis. So in a quasi-geostrophic context, the vorticity, the absolute vorticity here, changes following the geostrophic flow, but that's related to stretching by the vertical motion, stretching of vorticity. So where we've got ascent, we would get vorticity increase here, just on the warm side of the front. But in the semi-geostrophic formulation, that ageostrophic cross-frontal circulation is allowed to advect the vorticity and stretch it. So we get vorticity stretching here, but also advection here, which is increasing the gradient. And so, in fact, you can write the stretching at the lower boundary as being proportional to the vorticity, and therefore you end up with infinite vorticity in a finite time. So this was the main development of Hoskins and Bretherton.
What's gamma in
Oh, sorry, gamma is the strain rate in the deformation frontogenesis case. You can get something similar for the shear frontogenesis. It's a constant parameter. Yep. So that side of things we know quite well, although obviously that doesn't describe the formation of tornadoes and various things along the front. But now I'm going to talk about bent back warm fronts, and that relates to the new observations. So these are these kind of fronts that are wrapping right around the cyclone there. And clearly they've got very tight curvature. This is the same case. This is a radar rain rate, so you can see the cold front here. You have to imagine it's going off the radar quite literally and then wrapping round. This is the bent back front coming in over here in Scotland. And you can see this is now simulation on this side of surface level winds from the Met Office forecast. So you can see the extremely tight gradient across the front over the sea. That's the cold front. And then this gradient here is the bent back front. And then where the winds are black, that's pretty strong surface wind speeds. Unfortunately, there's been quite an observational development. So although this is only December 2011, so just 2 years ago, at that time there wasn't an equivalent wind radar observations for the UK, but now there is. So that's in the last year or so. I mean, had we been able to do this case now, then we would have had a better estimate of the wind fields over the UK than we had even just 2 years ago. This is the flight that we flew into the storm. So I was very, very fortunate to be able to lead this flight. It's very exciting. So we took off from Exeter and right into the centre of the cyclone, and then out across the southwest side of it. And you can see the flight tracks drawn over here over the forecast field. So we flew right into the cyclone centre and then out across the bent back front. And the way we observed the storm, we kind of dropped these sondes, so they're literally thrown out of the aircraft. And they give you vertical profiles down to the ground. And then we flew back at a lower level in situ, measuring various things to do with the wind fields and the cloud fields here. And then we did another flight in the early evening as the storm moved across. And these are the actual observations. So this is on this section from C to E going to the southwest across the bent back front. So this is the cyclone core here, and this is the, after crossing the front. So these are the observations from the sondes. This is a model forecast. You can see there are many things very similar. So the colour are the wind speed. So we've got very strong winds just on the cold side of the front. That's the front here. The front also slopes outwards radially with height, which is necessary to be in some form of gradient thermal wind balance. Some aspects of the model simulations aren't so good, and in particular it's the humidity field that the model struggles with, but I won't talk much about that now. And actually, just out of interest, this is what it actually looked like. So this wall of cloud curving round, that's actually that is the front, the bent back front, and it has some similarity to a tropical cyclone. So in a tropical cyclone, you similarly have a cloud wall that slopes outwards radially, but obviously tropical cyclones are much more circularly symmetric than the extratropical cyclones. But nevertheless, this wall is in kind of gradient thermal wind balance or near to it, and we have strong vortex stretching down here and frontogenesis at the eye wall here. So many things are similar, but of course the important point both of this cyclone and the extratropical one is that the curvature is very tight. So now we'll go back to a bit of theory. So the semi-geostrophic theory. So this is the 3D generalization of the frontal geostrophic theory. Hoskins proposed this in 1975. So many things are similar. You make the geostrophic momentum approximation, which means that you assume that the quantity that's advected in the momentum equation is geostrophic, but the velocity that you use in the advection operator is the full flow. And the way these equations are obtained, the approximation that you're making is that essentially the acceleration is much less than the Coriolis acceleration. And this chi here means the angle of the trajectory relative to the flow. So that the point is that the direction of a trajectory has to change much more slowly than 1 over f, or the rate of change is much less than f. So the timescale 1 over f is about 3 hours. So you kind of expect the Rossby number to be of order 1 if things are changing on that timescale. And clearly with these kind of storms, that is the case. So here's an example from Davis, Sher and Vernley quite a while ago now, in 1991, where they just illustrate for a barochronic wave what the geostrophic coordinate transformation does. So this is a semi-geostrophic simulation with kind of they've labelled X and Y in a rather unconventional way. So this is the meridional coordinates, and this is the zonal coordinates. And viewed in geostrophic coordinates, there's symmetry between the cyclones and the anticyclones. So this is the warm sector, that's the cold air coming down here, and you've got cyclonic and anticyclonic here. But when you transform into physical space, the regions of positive vorticity shrink relative to the anticyclonic regions. And this is really frequently, well, this is what's always observed really. The anticyclones are much larger with weaker gradients than the cyclones. So that's partly explained by the coordinate transformation and the semi-geostrophic balance. And here's another example from a later paper of theirs. It's a different type of model actually, but here you can see the cold front, the cyclone. That would be essentially the bent back front here. And then this illustrates, this grid would be regular in geostrophic coordinates, but it's been transformed into physical coordinates. So you can see how the coordinates kind of cluster along where the vorticity is strong, so along the cold front and then the bent back front.
I'm a bit confused.
Yes?
In 5 slides ago you said the gradient is more like squeezed at the bottom and then more expand on top. I mean, when you talk about the secondary...
Yes, that's right.
As a vertical direction.
Oh yes, yeah, okay. Well, that is a key point. What I was talking about first was just the frontal geostrophic theory, where it's assumed that there's symmetry in one of the horizontal directions, so along the front. And then I was talking about the cross-frontal circulation across that line. But in this more general semi-geostrophic theory, you assume the geostrophic momentum approximation in both horizontal directions. There is still vertical motion as well, but I haven't shown that. So it's three-dimensional. But actually, this plot here is actually for the wave on the lower boundary, I think. So this is the wave along the lower boundary. So you can think of the contours as being potential temperature on the lower boundary, and then the dashed ones would be the pressure field on the lower boundary. And similarly, this, where it actually says there at z equals 0, so it is on the lower boundary, but there is flow throughout the interior. And then as you said, the coordinate is bunching at the front here. So in the original frontal geostrophic thing, obviously this front would just be a straight line rather than having this curvature. And the point is, with the bent back fronts, I mean, clearly you can't ignore the curvature. So that kind of leads me on to this case study of bent back front, and actually some observations of what the wind field looks like. And people are obviously extremely interested in this kind of storm because this is what brings a lot of damage. So this again is the radar image, so this is real data but of precipitation rate, not the wind field. The storm centres here, cyclone centres here at this time, and you can see all this prominent banding to the south side of the cyclone, which is pretty typical in intense cyclones. So I'm going to think a bit about what that's associated with now. So here's some observations just from surface stations. So, you know, the UK is pretty well populated with surface stations, and this isn't all of them by any means. It's just, you know, it would be too messy if you plotted numbers all over the place. But the colours just indicate the time at which the maximum gust was measured at the station. So you can see that the storm gradually progressed towards the east-northeast, so the maxima are later over this side than on the west. And then the numbers are just the maximum gust speed in meters per second. So these are pretty strong for surface gusts. And then this time series is between Glasgow and Edinburgh, so in the populated lowland part of Scotland. And the interesting thing here is that there are very pronounced dips in the wind field with high gusts in between, and the timing of these is roughly related to the passage of the rain bands that you could see in the radar, although the phase relationships are not always precisely the same. But if you average over all the stations in Scotland, you find that on average the wind speed in the bands is less than between the bands. The difference isn't very large in the average, but that's partly because of various asymmetries and so on along the bands, so the real world is rather messy. But then if we look in the forecast model, so this is the new Met Office, well new, it's about a year old now, but the Met Office MOGREPS UK ensemble, which uses a 2.2 kilometre grid. These are 4 ensemble members from that run, and the colour field is the precipitation rate, so this kind of thing you can compare with the radar. It actually turns out that this ensemble member, if you look at the forecast over the day, it actually had considerable skill in comparison to the observed precipitation field and the banding. And in fact we showed that it has skill for scales of about 25 kilometres or larger, which is comparable with the band spacing in the across band direction. And then all these small lines have been drawn in here in these clear slots between the bands. If I skip to the next one, are actually all the cores where the wind field is strongest. So the model is getting some kind of very pronounced banding structure which is related to the rain bands, and it's within the bigger area of the storm where we'd expect the strongest winds. And this is very important for the insurance and impact side of things, because impact, people would say, scales as wind speed to the cubed. So, you know, a difference here of 10 meters a second makes all the difference in terms of damage. So there's a number of questions there. I mean, what is this banding? I mean, it's fairly generic in these strongest storms, but not very well observed. So Keith Browning talked about it with respect to one particular storm, where he proposed this idea of sting jets. So this is his schematic, where you have interleaving ascending and descending branches, and a likely candidate is conditional symmetric instability. So that's something you get if the PV, well, times the Coriolis parameter, is negative. I mean, the theory is generally for uniform PV, and people have also proposed that there might be an additional role of ice resulting in evaporative cooling, kind of enhancing the descent here. In actual fact, I won't show you here, that in this case that we observed, that evaporative cooling wasn't a big player. This is again using the model. So this is the kind of thing we can't observe directly, basically. So we have to use a combination of the model and observations. So here, that one of those simulations I showed you earlier is we interrogate the simulation and then look for regions which satisfy the necessary criteria for conditional instability. So that's basically that the saturation moist PV would be negative. So that's all these blue regions. There are some regions in green where the absolute vorticity is actually negative in the simulation, and people have argued before that if you have large amplitude kind of rolls or slantwise convection associated with symmetric instability, that would result in negative absolute vorticity. So for example, this green stripe here may well be a manifestation of a slantwise circulation in the model. And the slantwise circulations in the model tend to be rather weak, but that's partly a resolution issue. And then the red dots here are marking air parcels that come into the high wind regions to the south side of the cyclone. So this is some time beforehand in their history. And you can see how they come in round. All this fingering here is related to interleaving ascent and descent. So obviously the absence of cloud in the dry slots. And then these are trajectories in the model. So the black regions are where the trajectories are passing through the time frame where we actually made some observations with the aircraft, and then we're following backwards in time just by integrating trajectory equation backwards in time. And you can see just how tight the curvature is of the actual trajectories themselves. So for example, these ones here, which are actually ascending slightly as they come round, they're called the coal conveyor belt. And you can see they do a complete loop in about 12 hours. So that means that the rate of change of trajectory direction is faster than f, or comparable with f. So it's clearly Rossby number 1 or bigger. And these are the sting jet trajectories. The main thing about those is they're descending in towards the end as they come in, and they don't come round with quite such tight curvature. So I just thought I'd flag up some various other things that people have considered. So Mike Cullen proposed thinking about geotriptic equations. So they're ones where you also include some form of boundary layer and think about, so in this case they thought about vertical diffusion in the boundary layer. So that's what I've schematically put as the orange bit at the bottom. And the interesting thing about that, and I'm sure Mike will correct me if I'm wrong, that enhances the secondary circulation and the wind speeds that you get at low levels. So by adding in, essentially mixing in the boundary layer, you enhance the secondary circulation, which I think is pretty interesting because people have often talked about the fact that the strongest winds come in with descent, particularly in those banding structures.
We're going to say a bit more about that on Thursday. So
Okay,
that's a nice trailer for it.
Well, I thought you might do, yeah. yeah. And I particularly like that, although I believe your theory, you've all done it all in linear geometry so far, is that right?
So far, yeah.
And it would be interesting to do that for these tightly curving pieces.
Since you mentioned that, you can do the same sort of theory for a strictly axisymmetric flow.
Like a tropical cyclone,
That's
in
right.
fact,
That's done, essentially the same sort of thing. There's quite a challenge for almost axisymmetric flow, with obviously nothing is really exactly axisymmetric.
Yes.
And that's really an unsolved problem at the moment, because you have to somehow keep the flow almost axisymmetric robustly. So that's one of the big challenges. Can you really produce a sustainable model of almost axisymmetric flow?
Well, that's clearly very important with these extratropical cyclones. And one of the reasons they're not axisymmetric like a tropical cyclone is because they have a very fast phase speed. So the coherent vortex is rattling along about 25 meters a second in this case. So extremely fast.
That's a very challenging problem we're engaged on. Yeah.
Yes. And the last thing I want to say is a bit about balance and lack of balance, unbalance, I suppose. So this is the same case again, and you can see all this banding and precipitation. If you zoom in a bit, you can see actually, and it would be better if I showed a movie, but I haven't got one here. You've got some bands which are basically parallel to the bent back front, so this is this band of precip here. And then you've got other bands that are not parallel to it, and actually these white bands propagate out away from the front in this general direction here. And if we look at so now distance is running down here, and then time's running along that way. If you look at these kind of, Hofmuller plots or time-space plots, you can see how these bands are propagating away. That is the main bent back front up here. And these bands are associated with those wind anomalies. So they are of interest to people because of the quite large variations in the wind field at the surface. And so there are various things I could say about that. So Blumen, actually in a sequence of papers, kind of introduced an unbalanced frontogenesis model. So that was one with 0 PV, and then I think he went to a uniform PV kind of generalization. And in that, the front intensification is transient. It's to do with inertia gravity waves, essentially. But here in Cambridge, John Taylor and Callum Shakespeare have developed, I'm not sure whether they're here at the moment. No, I can't see them. It's a shame they didn't come along. So they've created a model which combines the balance model of Hoskins and Bretherton with the Blumen model. And I think that's got a lot of promise in it. It reduces to the balance model in the small Rossby number limit. But at Rossby number 1 or bigger, then you get a combination of balanced frontogenesis, intensification of the fronts, with radiation of inertia gravity waves. And although they've again looked in the straight front kind of scenario or geometry, I could imagine that kind of thing perhaps explaining what's going on here. But again, it's work to do. So I'll try and summarise some of those things. So first of all, I mean, sharp fronts form rapidly in the atmosphere. Everybody knows that. And the crucial thing is that there is a secondary circulation across the front. And the vortex stretching is always fastest near the boundary. The strongest wind region is not, well, sometimes it's on these long cold fronts, but normally it's on the bent back front coming around the cyclone. It tends to be on the south side because the system relative motion is adding to the translation speed of the cyclone. We find here for the most intense ones that it's definitely not in a small Rossby number regime, probably Rossby number 2 or something like that. And yet it appears to be near balance, but not exactly. The strongest winds occur in these mesoscale bands, and we think those again are related to conditional symmetric instability, although there are other potential mechanisms. For example, you get a lot of banding in the boundary layer over the ocean in the cold air, and some people think that that's convectively unstable and that the bands are related to a structure that already existed in the boundary layer and haven't formed through conditional symmetric instability. So we haven't quite got to the bottom of that. But personally, I think CSI is a more plausible mechanism. It may be stronger as a result of this semi-geotriptic balance that Mike's going to talk about on Thursday. And I'm very interested in this radiation of waves. So in particular in the forecasting context, people often talk about double fronts, which are very important for getting a weather forecast right, because you essentially get one band of strong winds and rain and another one behind, say an hour behind, and people haven't really understood why they occur, and that may be a combination again of a wave or an intensifying front. So I'll stop there, take any questions. Thank you.
Thank you very much, John. Other questions?
Yes?
So mathematically, balance is, if you like, asymptotic limits. So in any real case, you're never on, if epsilon equals 0, it's always something. You've sort of estimated what it is in various cases. So you will never expect to see a pure balanced flow because of that. You're always very likely that these near singularity will radiate waves in the real system.
Yes.
So,
I guess people have talked about wave capture and things as well, haven't they? I mean, it seems in this kind of case that these waves do appear out of nothing, and that you couldn't see them being vectored in.
You also have to be careful to trust, say, our numerical model output, how good it will be at the wave bit, because the resolution issue is resolution for modelling waves correctly is far more demanding than it is for the balance bit. But you will probably never really expect to see pure balance bit. The really interesting one is your bent back case where you say the Lagrange-Rossby number is much more than 1, but it looks like a balanced flow.
Yes.
It's not exactly axisymmetric either, and it's quite challenging to have something that's balanced and almost axisymmetric in a way that's sustainable. That's why I sort of made the comment earlier.
Well, it's clearly transient, though.
So that's the really interesting one, but it's not a wave. So understanding that better is a very good challenge.
Yeah, your bent back front, which is very nice and obvious there.
Yes.
How much is the bending back appearing in a horizontal plane, or is there some sort of vertical depth to the...
Oh yeah, well I can say a bit about that. So I didn't really explain these very well. So these, I mean, you can kind of think of these as the ensemble mean trajectory of a representative set of trajectories.
Yeah.
And so the ones that are wrapping, these are the ones that are in the air that's always near the bent back front, in fact just on the cold side, or what people tend to term the cold conveyor belt. So it's a coherent ensemble of trajectories, and they basically come in at very low levels here and they ascend slightly in their way round, but not by very much. So this axis is pressure, but they're going from the boundary layer to just above the boundary layer. And so typically these flows are quite shallow. They are quite near the boundary.
I suppose I was wondering how much are they like one sector of a helical structure, and what you're telling me is that not very much.
No, it's not the case that they'd be helical above that, really, no. And in fact, what happens is, I think it's partly because of the fast system motion. So the cyclone is moving very fast over this way. So these ones that are descending in just from above are much more open. So they come to a cusp here, and many of them come in from that way and then go around a little cusp and down there. And you can see a few are captured in that way. So there's a kind of hyperbolic point in here just behind the cyclone.
About the kind of wave emission, there was simulations in the 90s by Reed and Griffith of cyclogenesis, or rather, sorry, frontogenesis with in the primitive equations, and then
Yes.
they had waves emanating from
Yeah, well, yes. I mean, most of those that people have focused on in the simulations have tended to be. You have to imagine that there's an upper level trough here, and people have seen a lot of waves going from where the surface cold front is up to the region of the trough, and then into the stratosphere above. And so you just have to imagine the trough around here. These are much smaller scale. I don't think people have talked about those. In fact, this is the only. Well, let me get. I think this ensemble from the Met Office is the only time I've seen all this banding structure in an ensemble. And the advantage of having an ensemble is you can actually compare with the data in a meaningful way, because obviously there's a kind of chaotic sensitivity to initial conditions. So you need an ensemble.
You've got to be careful how well those things are really resolved in that model. So
Yes.
to what extent you really believe those. I know there's big uncertainties. You'd expect a big ensemble spread in something like that anyway, because of the
Yes.
uncertainties of the data. And then you're really once you get out of the balance regime, then you really need enormous resolution before you trust the results. That's one of the problems.
Well, that's right. But this is the surprising thing, though, that they capture the structure over the full 36-hour window in the ones that start off close. I mean, the ones that are further away, like this one, they obviously don't have any skill all the way through. So I think there probably is something in it, but that's something we're looking at the moment, is getting much more forecast statistics on that kind of phenomenon.
By following your talk, the sort of thing I noticed was this semi-geostrophy is kind of mesh adaptation capacity embedded from numerical point of view, because you stretch your coordinate and make it dense and dense. Is it kind of right interpretation, or
Well, you could.
show us on one slide how mesh is distributed after a while?
Yes, that's right. Yeah. So that's I believe how they did their simulation. I mean, I haven't done that myself, and so these are kind of more idealized balanced models. Of course, the forecast models are not balanced models. They're incompressible.
Compressible.
Sorry, compressible. Yes.
I guess question is, you wouldn't be able to run it forever, or I'm not sure. There's a life cycle, so the cyclone doesn't last forever. So you might be able to do it to the end of life cycle.
That's right. I don't think you could run this forever with that. I mean,
Yeah, I guess that's
certainly in the linear case, it would develop a discontinuity in a finite time.
so that should be a kind of limit of this semi-geostrophic.
No, you can run semi-geostrophic theory forever. I mean,
Yeah,
but I'm questioning whether it's realistic or not. It's another matter. But you can certainly run it forever. Yes.
I guess my question is how long, Mike?
No, well, there's an infinite timing, arbitrary long time existence proof for semi-geostrophic. So
Oh yeah, you got a proof for this?
yes, that was Benham and Brenier, the original result 10, 15 years ago.
But it's non-smooth, right?
Non-smooth, yes, non-smooth. It has singularities like those. Yeah.
So how long you can run?
Well, in principle,
Free.
Well, I'll show you on Thursday code.
Okay, wait for
40
that
days.
then.
I can run it for 40 days. You can run it forever. The issue is how much, the argument is whether you believe the answers, but you can certainly run it, there's no question you can run it forever.
Okay, so this is a good introduction for Mike's talk.
Yeah. Well, that's part of the aim, yes.
Well, yes, I guess one question is how good is the evolution that the semi-geostrophic?
Well, I don't know. I mean, we haven't tested that. I mean, as I say, the thing is, in order to use the new observational data, then we need the most realistic simulations that we can manage, and so we tend to use the operational forecast model because we know that verifies best. So I couldn't tell you what a balance model would do in the same scenario. And of course, all the diabatic processes and things are actually of order 1 importance. So that makes life difficult.
Well, anyway, as far as the mathematics, what I understand is that Thursday all that has been done about the semi-geostrophic should be presented, but
Yes.
of course then the matching with the experiments.
Well, I think the key thing that would help with new theory is thinking about curvature, but not exactly axisymmetric, as Mike said.
Well, that is very, well, I'd say it's certainly being studied and it's very challenging.
Any more questions? I don't know. Let's thank the speaker and all speakers in this.